So, hello everyone, good afternoon. Today we have the pleasure to receive Dr. Alexander Mead from University of British Columbia, and he's going to talk about the halo model and cosmological power spectra. Thanks a lot for accepting this invitation. Please go ahead.
Okay, well, good afternoon everyone, and thanks very much for the invitation. First thing I was going to say is, if it's easy throughout this, do not hesitate to interrupt if you have any questions, if anything I say isn't clear enough. Yeah, as I said, I'm going to speak to you about the halo model and cosmological power spectra, and this is some work I've done in the last couple of years, together with some of the collaborators you can see on the slide here. So just to provide an introduction to this, the work I do, the aim of this is to try and understand the distribution of large-scale structure, and by that I mean the matter distribution, in the late universe. And by the late universe here I mean redshifts less than around 2. So this is around the epoch of sort of dark energy domination in the universe. So we know from observations of galaxies that the galaxies aren't randomly distributed in the sky. The galaxies sort of trace out this cosmic web pattern, and we can see the galaxies. And we also know from other observations that these galaxies exist within a dark matter exoskeleton, which people call the cosmic web. So the form of this structure can be simulated relatively easily, but interestingly enough as well, it can also be measured directly via weak gravitational lensing. And it's known that different cosmological models, so for example different models of dark energy, predict quite different patterns for how the cosmic web would be distributed. And therefore it follows that if we use weak gravitational lensing to measure the cosmic web, we can use this to distinguish between cosmological models. The problem, while this isn't a trivial thing to do, is because structural formation in the late universe is complex, and it is non-linear. And by that I mean the deviation of a sort of patch of the universe from the mean density can be quite large. So if you think about it, the mean density of the universe currently is something like 6 protons per cubic meter, and things like galaxy clusters are very overdense compared to that mean, and there are similarly very underdense regions in the universe known as voids. Now the initial perturbation distribution of the universe, and that's something you can sort of see in the cosmic microwave background, which is shown in this picture here, is quite linear. So that means that fluctuations here that you see in temperature are small compared to the mean. So they're sort of something like 1 part in 10 to the 4 for the CMB. And that means they can be basically perfectly understood via linear perturbation theory. They also, the fluctuations themselves are Gaussian distributed. However, if you allow the density fluctuations, which must exist in order for the CMB to be splotchy like it is, if you allow these fluctuations to evolve and grow over 13 billion years, they become nonlinear and non-Gaussian. So this nonlinearity needs to be modeled if we're to use something like lensing to try and constrain cosmological models. And it's also necessary to model the distribution of structure as a function of model, as I was saying before. So you need to know what this should look like for any dark energy model, any modified gravity model you may want to constrain, or massive neutrinos. Say, for example, you could attempt to use the distribution of structure to put limits on how much mass neutrino species have. Is this loud enough, by the way? Is everyone able to hear?
Yes.
Okay, perfect. Good. I will keep going then. Right. So yeah. So this is. I'm just showing you here. The CMB is the sort of blotchy pattern. But as that evolves under its own gravity, you end up with something like the cosmic web, which is much more overdense. And this is what we can measure via weak gravitational lensing. So just to give a sort of very toy demonstration of how weak lensing works, what I'm showing you now is a picture of some pink dots, and these pink dots are supposed to represent some galaxies which are circular. So they're circular pink galaxies. And this is what they would look like if they're distributed in the way they are in a universe where there is no gravitational lensing. However, we know in reality that between us, the observers, and between those pink dots, there is large-scale structure, and we know that the light from those pink dots is going to be bent by the large-scale structure. So if we turn on gravitational lensing, this distribution turns into something like this. And what we see here is we see correlated shape distortions of the galaxies. So, for example, you see that the galaxies which were circular before have become elliptical, and we see that that ellipticity is in some way correlated across the sky here. And from this sort of this distribution of ellipticities, we can sort of use this to back infer what the mass distribution between us and those galaxies must have looked like to create this correlated ellipticity bending. Now, unfortunately, the cartoon here is greatly exaggerated, and there are sort of two big problems. One of which is that galaxies are not circular. So on average, a galaxy will have some intrinsic ellipticity, and also that the bending caused by the intervening matter is very small. So it's of order 1% of the ellipticity will be generated by this light bending, and a typical ellipticity will be something like 30%. So these ellipses will be sort of 30%. So we're looking for a very small effect here. So one way of trying to understand how fluctuations grow in the universe is to use linear perturbation theory. Now, linear perturbation theory can only be used when fluctuations are small, but it will prove to be a very useful thing to know about. So on the left-hand side here is the quantity we're going to be most interested in throughout this talk, which is delta, and I'm going to refer to that as the matter overdensity. So when delta is 0, the density is equal to the mean density. And when delta is positive, we're looking at positive departures from the mean, and when it's negative, we're looking at underdensities. And so that equation is given in the top left there. Below that, I'm giving you the equation for the evolution of linear perturbations in the late universe and at scales much smaller than the horizon size. So this is the only kind of relevant equation for like late-time nonlinear structure growth, linear order. And really we're just seeing that delta double dot, so that's kind of the growth of delta is proportional to the delta itself. So sort of structure grows when there's if you have a region of the universe where there's enhanced density, that enhanced density will cause structure to grow even more in that region. And the other term here you see is this 2h delta dot term, which is the Hubble friction term, and that arises purely because we're working here in co-moving coordinates rather than in sort of physical inertial coordinates. So that's a sort of kind of what you call it, like a fictitious Coriolis term that appears in these equations. So this is a kind of fairly simple linear differential equation which you can solve. And if we look at the universe when omega matter equals 1, so in the time when matter dominated the expansion of the universe, you get the solution to this, which is delta, the growth of delta is proportional to the scale factor. So what this means is that as the universe doubles in size, the perturbations themselves become twice as deep. So if the universe doubles in size, the universe doubles in size, and the perturbations themselves increase in strength. So you end up with a twice as big universe, which is kind of twice as crumpled at linear order. So that's good, but as I said before, that only works when the perturbations are small. And when perturbations are big, you have to resort to different techniques. So what I'm going to show you here is a plot, and we're going to be looking at rather a lot of plots like this throughout this talk. And this is a plot of the power spectrum of matter density fluctuations. And so I'm going to quite slowly go through this plot so that we're all on the same page from what I'm showing you here. So on the x-axis here, you see the Fourier wave number, which is k. So we imagine we're looking at the density field, which is a 3D thing that exists in co-moving space, and it's a function of, you can imagine the density being described as a function of x, which is your co-moving coordinate. Now, if you take that density and Fourier transform it, the Fourier transform variable, the conjugate to x is k. That is, so k is like a co-moving wave number here, and k goes as 1 over a wavelength. So on the left-hand side of the x-axis here, numbers like 0.01. If you imagine you have to flip that over to get some sort of physical thing. So that would be large wavelengths. So the small numbers, the small wave numbers here correspond to large wavelengths. And conversely, on the right-hand side, we're looking at high wave numbers, and they correspond to small wavelength fluctuations. So in order to say you had a density field, you could compute the power spectrum, you take that density field, you'd Fourier transform it, you then take that Fourier transform and its conjugate and multiply them together, wave number by wave number, and then to create this power spectrum, which is a function of k only, so it's not a function of k vector, it's a function of mod k, you would take every bin in your power spectrum that had the same mod wavelength, but they would all have different directions, and then you average over those in sort of annuli in k space. And in this way you could construct a power spectrum from some data or from a simulation. So that thing is what I'm showing at the bottom right-hand corner. That's pk, and pk is what's often plotted, but the actual thing I'm going to plot more often than that is this delta squared k quantity, which is the contribution to the variance rather than just the raw power spectrum. So in the plot we see two curves. We see the red, which is the linear prediction for what the power spectrum should look like, and then we see the black, which is from simulations, and that's a fully nonlinear cosmological power spectrum. So that's what the actual real universe's power spectrum looks like. So we can see kind of what you'd expect at very large scales on the left-hand side. The perturbations are all small amplitude, and the linear and the nonlinear predictions agree perfectly because there are no nonlinearities. But on smaller scales, so that's to the right-hand side of the plot, so that's larger k's, we can see that first thing is that delta squared becomes close to 1, which means we're looking at a regime where the perturbations will be nonlinear, and we can see that the nonlinear result departs significantly from the linear result. And we can attribute this to the existence of very nonlinear structures in the universe, things like halos. And these delta squared units, actually, what the physical interpretation of these is this gives you the contribution to the total variance in the universe per logarithmic interval in k. So what this is really telling you is that at large scales you're getting very little contribution to the variance, and that's because at large scales the universe is tending to homogeneity, the fluctuation is small, whereas at small scales you're getting huge amounts of contribution to the variance from all of the kind of very nonlinear structures that exist at that time. So that's great. So that's an example of a power spectrum. We can see a lot of plots like that. So in order to sort of compute those power spectra, and I should also say that this is very relevant to weak lensing, because basically the amount of distortion of galaxy shapes that you get is, you can relate it very directly to this matter power spectrum here, to this delta squared thing. So the next thing I'm showing you is we're going to talk about n-body simulation. So how do you go about computing this? So I said before, there's this one option which is linear perturbation theory, but this breaks down. So the sort of more brute force option is to use an n-body simulation. And in this way you represent the density field with n particles, and n in this case can be rather large. So typically you might be working with something like billions of particles. Then from the distribution of all these particles you calculate the gravitational forces between each one. You then move the particles according to those gravitational forces, and you just repeat this. And because computers are good at doing this kind of repetitive task, you can just feed this to some supercomputer and wait, and you get some results coming out of it. I've just also given you here the equation of motion for the particles the particles follow, and it's basically what you'd expect. It's acceleration is equal to the minus gradient of potential, and then there are the other terms, the 2h term, which again is a result of working in co-moving coordinates, and as is the 1 over a squared term. So we're just solving sort of children's physics, like force equals mass times acceleration, but in an expanding box. And this is the type of thing one typically, the type of density fields that one typically gets after running one of these simulations. So here I'm showing a slice through a simulation, and the simulation itself is 512 megaparsec cubed, but we're looking at just a thin slice through it, and I'm plotting the density. And so we see that this is the sort of cosmic web structure I was telling you about. You have areas in that which are very overdense, so the yellow regions represent overdensities of several hundred, and then you can see these kind of the blackish void areas, which are areas that have been evacuated of matter by the halos near them kind of sucking that matter out due to their enhanced gravity. One kind of interesting thing to note is that I've plotted this as on log for the color bar, so that we're looking at the log of the 1 plus the overdensity. And even the field looks kind of very non-Gaussian and non-linear in these units. So if you were to look at this in just sort of delta units, just without the log scale, it really is quite a sort of very non-linear field. Okay. So I mean, this in some ways this seems like a good thing, right? Because for any cosmological model, you can just run some simulations, and then you know what the nonlinear distribution of matter is, and then you can compare it to weak lensing. However, there are some drawbacks here, the limitations of simulations. So they're able to solve this gravity-only collapse problem to high accuracy. If you throw enough computer power at this problem, you will solve it. However, they are expensive, and to get the required accuracy, you need to run large numbers of simulations, particularly if you want to understand the covariance, but also just for the power spectrum to get the sort of average, get the mean of that correct. And people are looking at all sorts of kind of fun and interesting cosmological models, and it will never be possible to run accurate simulations for every model under consideration. The sort of ability of theorists to generate new models will always extend beyond the ability of computers to simulate cosmological models. And so if we want to investigate cosmological parameter space using something like weak lensing, which is entirely dependent on this nonlinear information, we need to do something about this. And just to give you a sort of flavor of the type of models that people are considering, there's the sort of bog standard vanilla lambda CDM paradigm, but within that, obviously, there are all sorts of different parameters you want to investigate. For example, you want to investigate how differences in the initial amplitude of the perturbations affect the nonlinear evolution. You want to see how small differences in lambda affect the nonlinear evolution. So even within lambda CDM, there are a number of parameters you might be interested in. You may also be interested in different dark energy models. Perhaps you're interested in ones in sort of some WA parameterization. Maybe you're interested in dark energy models where the dark energy interacts with some dark matter. And if these have nonlinear impacts on things, then you will need to simulate them. You also might be interested in massive neutrinos. You might want to see how they affect the distribution of matter, different types of dark matter. So, for example, warm dark matter, or you may be looking at some dark sector model where you have some dark radiation interacting with some dark matter and want to see what that looks like. Some people are also interested in modified gravity models. So these are models where rather than trying to explain the accelerated expansion with some dark energy or some lambda, you instead modify the gravitational equations themselves to see if some acceleration will arise naturally within those models. And again, if you want to constrain those, you need these simulations. The other thing I've listed at the end here is baryons. And even though that's not really a sort of extension to the cosmological model in any way, we all know baryons exist. The problem here is that the details of how baryons interact with themselves and how this back reacts on the dark matter distribution are not known. So, for example, things like AGN feedback, exactly how AGN feedback works and exactly how galaxies cool is not well understood. And often in most simulations, these sort of non-gravitational interactions are simply left out. So these need to be included somehow as well. Otherwise, you run the risk of mistaking your kind of exciting new dark energy model for actually, some AGN feedback in the universe, which is impacting the matter in a similar way to what you predict. So this seems a bit depressing now that I've talked all about this. So is there any sort of anything that we can take away, any positives we can take away? Well, one idea that presents itself here is if we look at the simulation again, but instead of looking at it in terms of the entire matter distribution, we try and identify the halos in that simulation. So we look for kind of spherical coagulations of matter, and we sort of identify them somehow and try and figure out their properties. So in this slide, I'm showing you the distribution of halos in the universe, and and each one is colored mass, so it has a color and a size according to the mass it has. So in this way, you can see that the halos themselves, they kind of basically trace the same cosmic web structure that you can see in the overdensity, and you can see that you get filaments in the halos as well, and sort of you have halos of different sizes, and you have many more low mass halos than you have high mass halos. So this all sort of presents us with an idea in that maybe we can try and understand the nonlinear power spectrum and understand the clustering of matter by decomposing it into two bits, some bit that's coming from the halos themselves and some bit that's coming from the halos with respect to one another. So this is the kind of basic idea behind the thing that people call the halo model. And really the halo model is just a sort of catch-all term for any model of anything in the universe that sort of relates some observable you might be interested in to the properties of the underlying halos. And it really comes around because if you run cosmological simulations and you look at the output of them, you see that the matter is kind of clumped into these kind of fairly spherical bits. So if you understand those spherical bits and you understand how each of those changes with your underlying cosmological model, then perhaps we can work out some way of figuring out what the overall clustering looks like in this sort of decomposition. So I should point out as well, this is often confused with something called halo fit. Now halo fit is a fitting function that people use to for the nonlinear power spectrum. But it really is, it's just a fitting function. It's some formula with a number of free parameters, with something like 30 free parameters in it. And that formula was fitted back in 2003 to a host of n-body simulation data. Whereas what I'm talking about is really, it's like a model where we really keep track of the physical properties of halos in the universe. So the equation you see in the middle of this slide is a representation. Well, it's the equation of the halo model. It's saying we're looking at the power spectrum, delta squared k, and we're going to say we're decomposing that into this part, the 2 halo term that comes from large scales. And we think probably large scales, well, from what I showed you before, that looks a lot like, it agrees with linear theory on large scales. So we're going to say large scales, maybe linear theory gives a good description of the clustering. Whereas at small scales, we get some contribution from the halos. So a very simple form for the 1 halo term is given below here. And in that one halo term, we're writing the contribution to the clustering as coming as an integral over all of the halos. So I'm just going to go through this equation very, very briefly. So all the pre-factor outside the front of that, the 4 pi k over 2 pi cubed term, that is all just a result of converting from p of k, the standard sort of power spectrum, into this delta squared units. So the really interesting thing is the integral here. And what this is saying is that this is an integral over f of m dm. So f of m here is what's called the mass function of dark matter halos. So that's some function which tells you how many halos you expect to be of a given mass. So it's a function that peaks, well, it's high when the mass is small. So you have many small mass halos, and then you have fewer high mass halos. And then the other term you see in that integral is just m times w. Now m times w is just a funny way of writing that thing is the Fourier transform of the halo profile. So what this is saying is we get the power spectrum as arising from halos. It's just integrating over the halos of all different types of mass times the halo profiles, which is what you'd expect, pretty much. So it follows that if we know these ingredients, so if we know the mass function and we try and find out what the Fourier transform of the halo profile looks like, we can have a guess at what the power spectrum might be doing. So I've just highlighted those ingredients on this next slide. So at the top we have exactly the same equation that was on the previous slide, and below that is just a list of the type of ingredients you need in order to be able to calculate this integral. So at the top we have the halo mass function. So this has been measured in simulations, and how it adapts to changes in cosmology is well understood. Now the halo mass function is written usually in terms of this new variable rather than mass. So we need some way of converting between this new variable and mass, and how that new relates to the mass is given in the second equation in that list. So new is given by, it's inversely proportional to sigma of m, and sigma of m is just the variance of the universe when smoothed with some filter which encompasses a mass of m. So that's understood. The next thing we look at is the halo density profile. So often people use the NFW form for this, and that's what's shown here. be a good match to simulations basically independently of the underlying cosmological model as well, which is very lucky in a number of ways. But it seems that if you add, you can add all sorts of sort of strange ingredients to the universe, and the Halo density profiles are fairly insensitive to what you're doing. We need to truncate those Halo profiles at some virial radius, so that's the next thing down there, RV. And that's related to this delta V thing, which gives you sort of typical density of halos. And then this halo profile also has this RS number in it, which is sort of some sort of scale radius for the halos. And that's related to the virial radius by something called the concentration parameter, which is given at the bottom there. So the concentration, and the way that that varies is also understood, and it's known to the concentration of halos depends really on their formation time. So all of these things have been investigated in the literature for the last 20 or so years, and are fairly well understood. So we're able to, so now if we look at the next slide, we look at, we're able to sort of compute this integral because we know these things like the math function and the halo profile. And this is what you get as your prediction for what the power spectrum should look like. So what we're seeing here, the blue curve that we see is the one halo contribution. So that's the power that arises from the clustering inside halos. The red contribution here is just simply the linear power spectrum. So that's the power spectrum you get of mass fluctuations from inflation at the far left-hand side. And it tilts over as those fluctuations from inflation get changed, get processed during the early radiation-dominated epoch of the universe. And the Halo model simply says, well, we should sum these things together, and that will give you basically what the full total mass power spectrum should look like. So that's shown by the black curve here. And again, it's sort of it's nice because it's kind of what you'd expect. Far left-hand side, so at very large scales, the power is basically given by the linear theory, whereas at small scales, we get the power almost exclusively comes from the contribution from halos, which is kind of, I guess, naively what you'd guess. So this is kind of good, and maybe at this point you think the problem is solved. We now have some recipe that converts halo properties that we think we understand how they vary with cosmological model to a power spectrum. So this means we can know what the power spectrum should look like as a function of cosmological model, and therefore use this to sort of constrain cosmological model using Reed lensing. However, unfortunately, this is not quite true. So the next slide I'm showing you is a comparison of that sort of simple halo model prescription I gave you to n-body simulations. In this case, you can pretty much regard n-body simulations as giving you the truth. Their accuracy has been tested enough. People have looked at convergence properties of these things. And so the simulations really tell you what the truthful nonlinear power spectrum should look like. So that's the crosses in the top panel here. And the solid lines give you the halo model prediction for that power spectrum, whereas the dashed lines show the linear theory. And what we can see from this top panel is that while the halo model is kind of qualitatively correct and gives you a fairly good idea of what this power spectrum looks like, it's wrong in detail. So in the two lower panels, I'm showing you the ratio of the halo model to the simulation prediction, and we see that there are some various deviations at the kind of 20% level, both redshift 0 and redshift 1, and this is bad because current weak lensing surveys that are sort of active at the moment, so for example the KIDS survey and DES, which is on the way, measure correlations in lensing that require accuracy in this power spectrum of around 5%. So these sort of 20% deviations we see here are completely unacceptable. So this is a big problem. So maybe you think at this stage, well, I made some choices when I chose my ingredients for the halo model. What happens if I change those choices? So for example, I used a particular form of the mass function. I used actually quite an old mass function. It was 1999 Sheth and Torman mass function. Maybe if I use the Tinker mass function instead, that will improve things. So let's just go. So if I go from what I had before to the Tinker mass function, you can see the form of the power spectrum changes a little bit, but there are still these kind of fairly gross inconsistencies which seem not to be remedied by this. The other thing I can do is maybe change, say I used a fairly old form for the halo concentration mass relation, that is how concentrated halos should be as a function of their mass. Maybe I use an old-fashioned one and maybe newer ones are better. So here I use a newer concentration relation from Duffy. And we can see once again that you get some small differences in the power spectrum, but you wouldn't necessarily say they were huge improvements, and they certainly don't go very far to remedying these sort of glaring errors in the calculation.
Can I ask a question?
Yeah.
I have two questions actually. One relates to the halo bias. So you have to, for each mass function, you have to define a halo bias as well. You have to calculate the halo. Okay.
So in the form of the halo model, which is sort of often written down, sure, there is this halo bias term, and what that, I haven't actually included that here, but what that does is takes that 2 halo term and sort of damps it off at small scales. Now it turns out that this really, it doesn't matter very much at the level of the full power spectrum, because the point at which that bias term damps off the power is where the 1 halo term pretty much dominates the power anyway. So really, I mean, and the other thing is that sort of the standard expression that people often write down assumes linear biasing.
Yes.
And on the scales where this whole model starts to break down, so really you can see from these plots that the breakdown really occurs in this kind of transition region between the 1 and the 2 halo terms. In that region, you really need sort of non-linear biasing prescriptions, because the real thing that you want in the halo model is actually the power spectrum of halos. So you need to somehow relate the power spectrum of halos to the power spectrum of matter.
Yes.
And so in this region where there are problems, you need all these kind of non-linear biasing prescriptions, which are often not included.
Okay, and the second question, in this plot that you show, when you compare z equal zero redshift, for instance, today, I would expect that at very large scales you would go to the linear. But so for z equals 1, it seems to go to 1, but for z equals 0, no.
So this kind of illustrates an odd feature of the halo model. So if I go back here, so this is just this shows you the full power spectrum, and it's how it's composed of the 1 and the 2 halo terms. And you can see that at very large scales, the 1 halo term has this kind of power law form, and actually the slope of that power law is such that it's less steep than the slope of the primordial spectrum. So the primordial spectrum, you expect the P of k to be proportional to k to the 1, more or less. But actually this P of k that you get from the halos is proportional to k to the 0. So at some point, it's not shown on this plot, but in very, very large scales, like extraordinarily large scales, this model would predict that the 1 halo term would once again take over from the linear theory. Now, this can't possibly be correct, and what's going on here is that there's this flaw in the halo model when you first write down the equations, and it really kind of implicitly you're only accounting for positive perturbations, so you don't conserve mass in the way that you should. And in the power spectrum, this results in this shot noise form, what's called a shot noise form, this k to the 0 spectrum at large scales. Whereas in the correlation function, that all goes into a non-zero correlation function at zero lag. And really, for like a cosmological correlation function, that number needs to be 0, and this shot noise term should vanish as well in the power spectrum. The problem here is that any anything people have tried to do to remedy this problem, to sort of try and account for mass in a better way, breaks some of the other nice features of the Halo model, so it really kind of upsets the other predictions it makes for the matter clustering. So it's often just this problem is sort of known but ignored. So the way that manifests in the slide I was just showing is at redshift 0, you're seeing this not go to 1 because you're getting some small contribution from the one Halo term at these very large scales, which is unphysical.
Okay.
And that's again, that's responsible for that like extra bump that you see even but like around k of 0.1. So on scales much below that, where you'd really think linear theory should do a pretty good job, you're getting like a 5% excess in power just because you're getting this unphysical contribution.
Okay, thanks.
Okay. So on the right hand side are listed some other problems with this sort of standard basic Halo model that I've talked about. So what things that we haven't included yet, which one of which would be perturbation theory at large scales. So a lot of people go to a lot of trouble to do these kind of slightly beyond linear calculations of what the matter density field should look like, and there's no way that's been included in this simplistic prescription I've given you before. There are, if you think about the transition region and you look at the scales that that corresponds to, there are various things that you know will contribute to the distribution of matter at that scale that are not included. So for example, voids and underdensities, and at these type of scales we also need to include the way that the halos themselves are not linear traces of the matter field. In fact, there'll be non-linear biasing there. We also haven't included any sort of filamentary structure in what we've done. We've assumed halos are spherical, and clearly if you look at enough simulations you see this really isn't true. And not only are these halos not spherical, actually the asphericity of them is aligned. So you imagine some filament and you have halos along that filament, and those halos will be tidally aligned with one another. We've used halo profiles that are correct for, or have been identified in simulations for virialized objects, so very relaxed, isolated systems. And obviously there are contributions to the density that arise from things that are not virialized particularly. They may even still be in the process of collapsing. At the moment there's been no inclusion of halo substructure, and we've also assumed that for a given mass halo, all halos are identical, so the mass fixes all of the halo properties. Whereas in fact you can look at halos in simulations which are of similar masses which have very different properties. Say for example they have different concentrations. And this has been ignored as well. So at this stage there are sort of two things, well, there are two things one could do. Ideally we want to try and remedy these inaccuracies of the Halo model without breaking its nice features, and the nice features are that you can relate physical properties of halos to the nonlinear power spectrum in this case. Now we could try and sort out all of those problems individually on the previous slide that I talked about, but this would be hard to do, and people have tried various attempts to solve various things, solving some of those problems, and the equations become much more complicated very quickly. So instead in this work what we're going to do is we're going to opt for the much simpler goal of looking at what I'm going to call effective halos. And these halos will be different from real halos in some way, but when we apply those equations, the standard Halo model equations, to them, we hope that these effective halos will have a power spectrum that accurately matches the simulations. So this is going to involve some fitting. We're going to introduce some numbers, and we're going to try and do this in such a way that those numbers don't break this sort of lovely kind of physical form of this Halo model. So there are a few things one can do, and here just I'm giving a couple of examples. So there are certain numbers that go into these Halo model arguments that are kind of round numbers that are motivated by analytical arguments. And really we can kind of see what the effect of changing these numbers is on the Halo, on the power spectrum. So in these plots I'm always showing the power spectrum relative, so divided by the power spectrum at some midpoint. So in the top left-hand panel I'm showing what happens if you allow the virial density just to vary freely. So I'm changing it from its fiducial value of 200 up to 400 and down to 100. You can see how this impacts upon the power spectrum. The thing in the bottom right-hand panel that I'm showing is the same thing, but if you vary this thing called the linear collapse density, which relates this variable nu in the mass function to the mass itself. And you can see that varying both of these things have fairly large impacts on the power spectrum. So we can hope that by introducing some free parameters and maybe fitting these to simulations, we can improve things. And indeed, that's true. So on this next slide, I'm showing you what had happened before. With the solid lines are the power spectra as they were from the sort of standard vanilla Halo model calculation. And the dashed lines and the bottom two residual panels are showing you the power spectrum if we allow some parameters to be free and fit to the data. And you can see that we provide, you know, you can match simulations at the sort of more like the 5% level by doing this kind of fitting. So on its own, this wouldn't be that impressive because here we're just looking at one simulation of one particular cosmological model. So what you really need to do is introduce several more free parameters and fit them all to a whole slew of simulations. So that's what's shown in this next panel. So here I'm showing comparison of 37 different simulations. So again, we're looking at residual power spectrum of the model to the simulations. And each colored line in each of these plots shows a different cosmology. And the thick black line, it shows the sort of the average here. And we're going from redshift 0 on the left to redshift 2, and we can see that if we introduce, in this case, something like 7 free parameters and fit them to data, we're able to get power spectra that are accurate at around the 5% level. So as well as those two numbers that I showed you in the previous plot, several other numbers were allowed to float in this. So for example, there was a term to damp off the there was an extra parameter that was used to damp off the one halo term at very large scales. So this is addressing the problem that was mentioned in the question before. So at very large scales, there's just some term to damp the power spectrum there. Also the transition region, which is this region of the halo model that is particularly problematic, has been remedied by just kind of smoothing that transition in some way. So this isn't, you know, this isn't like a particularly elegant solution to this problem, but it's remarkably works remarkably well. And so the top panels I show here the halo model predictions, whereas in the lower panels I show predictions from halo fit, which is the sort of Takahashi et al. Variant of that. And halo fit here is just this fitting function for the power spectrum. So you can see that by doing this we improve a little bit over the halo fit description. So that's good. The nice feature of doing this, the sort of so while this sort of small improvement over pre-existing things is nice, it's clearly not, you know, it's not revolutionary. But the nice feature in doing all of this work, in that we still have the equations we solve at the end of the day still relate to halos, and we relate the power spectrum to those halos. And so we're still able to sort of exploit the physical nature of the model with the caveat that we have sort of messed around with it a little bit. But one thing we can start to look at is something like baryonic feedback here. So we know that in reality a lot of the simulations that I showed in the previous slide are run assuming that gravity is the only important interaction in the universe. But it's known that there are baryons in the universe, and it's known these baryons, you know, gas cools, AGN feedback occurs, and this redistributes matter in some way. It turns out, somewhat remarkably, that the effect of this baryonic feedback on the scales that are sort of relevant to weak lensing can really be captured by changes just in the halo profile itself. So what you can really think about going on here is that gravitational collapse really forms the halos in the first place and moves them in the ways that they're going to move. And then baryonic feedback happens a bit later and really just changes the properties and the internal structure of those halos. And there are some nice papers by Marcel van Dalen which sort of demonstrate this kind of explicitly. So really it seems that we can sort capture the effect of baryonic feedback on the halo population by just changing the internal structure parameters a little bit. So in this case, I'm showing you what happens if we just allow this A parameter that comes in the front of the concentration mass relation to vary over some range. And we can see that that causes the power spectrum, as A increases, the concentration of halos goes up, and as you expect, that causes the power to increase, whereas if you decrease A, you decrease the power. So it follows that we can hope to sort of encompass baryonic feedback just by some change in the concentration parameter here. It actually turns out there's another parameter. You need the concentration, doesn't quite tell you the full effect. There's also another effect which tells you another parameter we use which kind of bloats the halos or anti-bloats them in some way. But with a combination of these two things, you can pretty much account for what's seen in hydrodynamical simulations of baryonic feedback. Sorry, my ability to change slides has changed. So here I'm just showing you, again, on the left-hand side, we're looking at the power spectrum, and the three colored lines are simulation results from different hydrodynamic simulations that assume different feedback mechanisms. So you can see that basically these feedback mechanisms tend to damp the power, and that's because they really take a halo and bloat the inside of it out a bit as it sort of fills up with gas, and that drags the matter around with it. And then it turns out by changing some of these structural parameters of the halo, you can fit all of these baryonic feedbacks to within 5%. Now that's what's on the left-hand side. On the right-hand side of this plot, I'm showing you the psi plus and psi minus functions for lensing. If you don't know what they are, it doesn't really matter. But this is just basically what weak gravitational lensing surveys measure. So the points with the error bars are measurements from the CFHT lensing survey, and the red curve in the top panel and the orange curve in the bottom panel show you the best fit cosmology to this from CFHT lens, so the best fit correlation functions that they use that's found from that survey. And the thickness of that line just shows you the amount that baryonic feedback can vary those correlation functions. So you can see at the moment for something like CFHT lens, the baryonic feedback isn't particularly important. And really, so the other line I show, the pink line above that is the best fit Planck cosmology, which has a kind of considerably higher sigma 8 times omega matter number. And you can see that baryonic feedback does nothing to alleviate this fairly big discrepancy between the two different cosmological models. But anyway, this having these numbers in the modeling now allows you to to basically account for the effect of baryonic feedback on your weak lensing measurements. So that's what Shahab Judaki has used this for in his fairly recent reanalysis of the CFHT lensing data. So he's used this header model that we developed, which is called HM code, and has allowed these baryonic feedback parameters to vary freely and be chosen by the data, and then he's marginalized over them so that the constraints no longer are sort of biased by our ignorance of baryonic feedback. So on the left-hand side, we're looking at constraints from lensing and from the Planck satellite in the omega matter sigma 8 plane. And this banana feature that you see is the degeneracy, like the lensing degeneracy, which you get because the same amount of lensing can be caused by either a high sigma 8, that's a high amplitude of fluctuations, with each one with a lower matter density, or else with a lower amplitude of fluctuations, but each one with a higher matter density. So that explains the degeneracy direction. And what you can see here is that on the left-hand side, you see the difference between using HM code, that is our halo model, versus halo fit to do these constraints. So you can see they agree kind of, more or less, but there's some small differences which are caused by the sort of improved accuracy of the halo model approach. And on the right-hand side, you see what happens when Shahab allows the baryon parameter to vary. So if you use uninformative priors for that, you get the green ellipse. Whereas if you use these informative priors where you say, well, we're only allowing that number to vary in kind of a way that we're informed by these hydrodynamic simulations, you get the orange ellipse. And so it changes ever so slightly from if you just fix the baryonic feedback. And you can see that none of this really goes very far to alleviate any of this tension that seems to exist between the weak lensing measurements and the measurements from the Planck satellite. So just to sort of show you another few features of this approach, because we sort of maintain all of the nice ingredients of the halo model, and we maintain the kind of physical description it has of clustering, we're able to extend this approach to other things fairly easily. So here, for example, I'm showing you the ratio of power spectra to a lambda CDM model from dark energy models, for various dark energy models, which I parameterize via this WBA parameterization. So the crosses show you simulation measurements, and the solid line shows you what the halo model predicts for the clustering, and the dashed line shows you this halo fit approach. And you can see that in all cases we do fairly well, and this is without adding any extra free parameters at all. That's because this model is sort of well-founded and well-motivated physically, so the power spectrum responds appropriately and changes to the underlying cosmology. So that's good news. Then the final thing I'll show you is for some massive neutrino models. So what's going on there is most simulations are run assuming that all of the mass in the universe is in dark matter, but if neutrinos have some mass, then at late times they become non-relativistic and they have some small contribution to the total matter density. And what this tends to do is to damp the growth of perturbations, because those neutrinos were initially relativistic, so they were free streaming in the same way that radiation does in the early universe, and so any perturbations on small scales in the neutrinos were erased. And then when they become non-relativistic, then they just behave like normal matter. But this means that for fixed total matter density, if some fraction of that matter is smoothly distributed, then that will retard the growth of all fluctuations. So this can be, you can solve some linear equations for this, but you can also run simulations of these things. And once again, if you ask the halo model what the power spectrum should look like, you get the answer quite correct. So I'm showing you in each of these plots, each one shows a different neutrino mass, and on the left-hand side we're looking at redshift 0, on the right-hand side we're looking at redshift 1. And we can see that the halo model does a fairly good job of predicting what the simulations show, which are the blue points.
Question?
Yeah, of course.
In this case of massive,
sorry, can you say that again?
In this case of massive neutrinos,
yeah,
the one term does not change.
It does change. So because the linear power spectrum changes. So if you compare a model of if you compare a model with two models which both have fixed total matter density, but one has some small fraction of the matter in massive neutrinos, then the linear power spectrum will be different. So that's basically what's shown as in the red curves here. Now, the one halo term depends on the linear power spectrum through the halo mass function, because the halo mass function itself depends on the variance in the linear field when smoothed on scales corresponding to the mass of the halos. So in this framework, the one halo term is automatically suppressed when you include the massive neutrinos because of that.
Okay, and do you assume that the profile does not
yeah, so yes. So the profile, I'm just trying to think if there's any way, the profile might automatically change a little bit, because the way that I use the concentration mass relation depends on the growth history. So there might be very small changes in the halo concentration. But other than that, the halo profile itself doesn't change at all. There was... No, I don't think it does. So in reality, I mean, in really what you'd expect for each dark matter halo in a universe like this to be kind of surrounded by a neutrino halo. But because the neutrinos, for like these kind of cosmologically interesting values of the neutrino mass, are only a very small fraction of the matter, you can ignore this in a way that that seems not to matter at the level of sort of a few % accuracy anyway. Does that make sense?
Yeah, okay, thanks.
Okay. So I think I'm more or less out of time, so I'll just summarize this then. So by using the halo model and adding some fairly physically motivated free parameters and then fitting these to high resolution cosmological simulations, we're able to make predictions of the matter power spectrum that are accurate at around 5%. And 5% is a good number because that's basically the accuracy that's lower than this. Well, it's lower than the statistical accuracy of current weak lensing surveys. So, for example, this is accurate enough for KIDS and for DES. Now, it won't be accurate enough for things like Euclid and LSST, but you know, that's a few years away yet. And we're able to do this across a wide range of cosmological models, and this includes things like massive neutrino models and various different dark energies. So there's links to a couple of publications there, and the code for this is to carry out this calculation is available at that link that's given there as well. It's also, this model is now integrated within CAM into the HaloFit PPF module. So if you use CAM, it's the latest version. You now have the choice to use this calculation for computing nonlinear corrections there. So this can be useful for either weak lensing or for CMB lensing or something like that. And it's relatively easy to add standard model extensions within this framework. You're not guaranteed to be accurate, of course, but it's quite easy to sort of go beyond this. I did have a load of extra slides, but I won't go through them on some further work that I've been doing more recently, which is trying to come up with % level accurate power spectrum predictions. But I will stop there. So thank you.
Okay, thank you very much. Very nice talk. So we have time for questions.
So yeah, maybe I have a little question.
Yeah.
Can you hear me?
Yeah, absolutely.
So yeah, so I was just wondering about what's the specific failure of the Halo model when you compare it to simulations. I don't know if maybe this is a very basic question or I don't know, but the point is that if you take a simulation, a very high resolution simulation, and you, for example, detect your halos in some way, because, and this is part of the question, these discrepancies could not be related also with the way in which you detect actually the halos on your simulation. But let me just finish. If you detect the halos, you measure everything. I mean, you can measure the power spectrum, you can measure the profiles of the halos, you can measure the concentration as a function of the mass of the halos.
Yeah.
You use exactly what you measure and put it into the Halo model. Yeah. And then you compute the Halo model prescription for the power spectrum. It doesn't work. It should not work. That's my question.
It won't work. So the problem is, I mean, what that sort of vanilla Halo model calculation, you're assuming that all of the mass is kept in these nice virialized halos, and you're assuming that those halos themselves are linearly biased with respect to the underlying matter in that calculation. And clearly these things aren't true. So obviously there are nonlinear biasing effects for the halos going on. You're ignoring other contributions, definitely very nonlinear structures. So for example, things like filaments, that you're ignoring them. You're also in that sort of, at least in that standard calculation, and there are ways to remedy this, but you're ignoring scatter and halo properties at a fixed mass. Now, with what you're saying, when you run a simulation and you measure all of these things, you could measure that scatter and somehow include that in the calculation. But clearly that's a thing that's part of that nonlinear density field that you haven't accounted for by this simple calculation. Also, substructure is usually at least not accounted for. There'll be other sort of unvirialized conglomerations of halos that somehow aren't accounted for. So the main way all of this stuff manifests itself is in this transition region between k of say k of 0.1 and 1, which is the real sort of regime in which the halo model sort of doesn't work properly. Whereas you see at sort of smaller scales, it tends to work better, and that's because really at those smaller scales you really are looking at just the dense parts of the matter field. Does that answer your question?
Yeah, sure. And then maybe the point is that there's no unique phenomena determining the failure of the halo model. I mean, you have all of these problems mixing together.
Yeah, true. So there are ways of assessing this. So I think it's not true to say that all of these problems are of the same magnitude. So for example, this idea of halo, like tidal alignment of halos. So one thing I did at one stage is if you take a cosmological simulation and identify the halos using some method in it, and you try to break this tidal alignment. So for example, if you take each halo and just rotate it by some random amount, by some random angle in some random direction, that will break any correlation in the tidal alignment. And then you can measure the power spectrum before and after doing that and sort of see what happens. And basically, that tidal alignment contributes only something like 1% at the type of scales you're interested in. So clearly that's not a very big effect. Still obviously important if you're worrying about things at the percent level. Whereas I think things like, for example, particularly the nonlinear biasing and not including sort of perturbative corrections to linear theory, these kind of quasi-linear perturbation things at large scales are much more important. So not having those included, I think, is one of the big problems. I mean, there's also been some recent work by Ross Seljak and some people, I think, trying to look at improving the halo model in these particular regimes. But in their approach, they, rather than keeping the one halo term intact in the way that I've done here, they take the one halo term and decompose it into just like some power series, and then fit those power series term by term. So in this way, they're able to get fairly accurate fits to simulations, but they've sort of broken the predictive power that's inherent in the one halo term. So you're no longer able to say, gauge what would happen if you make some change to the mass function.
Okay. Thank you very much. Very much.
Okay.
Alexander, I have a question here. Just a quick one. So when you show the banana plot and the analysis of a CFH-ALS, and there was this tension with Planck, yeah, that's right. So there is this dark energy survey size verification cosmology paper, right, Abbott et al. And so do you have any comment on that? Where what happened that the tension's gone there between the I think there is a kids paper, recent paper also where it's gone, right? So
no, I think in the recent kids papers, this tension remains.
Oh yeah, sure, yeah, that's right.
So on some level, like so I'm loosely associated with kids, and I sort of don't want to get dragged down into the kind of politics of this, I guess, on some level. I think from what I remember in the DES science verification paper, their error bars are large enough that they are in agreement with both Planck and the previous CFHT lens.
That's fair, yeah.
Measurements. So I think from that science verification data, one can't sort of make any comments on whether there are any systematic effects in any data sets or anything like this. I'm trying to remain sort of what's the right word, like agnostic here. particularly because I'm not an expert on the actual observing and these kind of things, these sort of systematic effects, either in the CMB measurements or in the lensing measurements that may go into this tension. I mean, the other thing I would sort of bear in mind is there seems to be some level of disagreement on exactly how much tension there is, and you have some authors claiming things like 7 sigma, whereas you have other people complaining. You have some people saying things like 7 sigma, and you have some people who say that there's actually no problem at all, and statistically these things are not discrepant. I mean, it looks to me like there is some discrepancy, but I try to keep like an open mind about these things.
Okay, thanks.
Does that make sense? Yeah.
More questions?
Yes, I have a question about warm dark matter. So there are several prescriptions. There are several prescriptions to change the halo model in order to take into account warm dark matter.
Yes.
Can you comment on? We're familiar with one by I think Ariel Schneider. I think he proposes something called sharp K window function.
Okay, yeah, I vaguely remember reading this. So I think that, I mean, the one paper I'm sort of more familiar with is there was a Robert Smith paper, maybe a 2011 Robert Smith paper, where he looked. And then also quite recently, Doddy Marsh. I don't know if you know him. He sort of adapted the code I wrote to make the power spectrum for warmed up matter models.
What's the name again?
Doddy Marsh, David Marsh.
David Marsh, okay.
Yeah, there's a paper that's title is something like Warm and Fuzzy, and he's particularly interested in the...
Yes, I know this paper, yes.
Yeah, yeah. So my memory of this is that, so technically with these warmed up matter models, there are, you have a suppression of halos below some limit. So rather than, in cold dark matter, you think the mass function sort of continues ad infinitum to low masses, and you have sort of very large numbers of low mass halos. I think the expectation in warmed up matter is that you don't get any of these sort of low mass halos. And there are also some number of other things. So for example, you expect the warmed up matter to affect the halo concentrations in some way. My memory of this is that you basically get the answer almost, you get a good answer to some good level of approximation just by including the warmed up matter linear spectrum in your calculation. So when you just put a linear spectrum with a cutoff through this whole halo model apparatus and sort of crank the handles, the answer you get isn't too bad. And if you then further go on, and so in doing so, you automatically get a mass function which is suppressed. It turns out it's not suppressed in quite the same way as the suppression that's seen in simulations by doing that. But even if it seems that the improvement you get by adding this adding this cutoff in the mass function is quite minimal at the level of the power spectrum.
Yes.
So I'm definitely, these additional things are not important, but certainly if your interest is in the matter power spectrum, I think you can go a long way just by including the linear theory suppression.
Okay, thanks.
Okay, any other question? Okay, so I want to thank Alexander again. So thanks a lot for this talk.
No problem. Well, thank you very much for inviting me.